Hello, and thank you for joining us for today's Talking Medium Voltage webinar. We're coming to you from the NHP Power Hub, which is located at the NHP head office here in Richmond in Victoria. So if you'd like to come down and visit the Power Hub if you're in Melbourne, please get in touch with the people here at NHP in Melbourne. Now, my name is Nicholas Burley and I'm your host today, but I'm being joined by a panel of medium voltage experts. So first with me today, joining me in the Power Hub, is Dmitry Lazarchuk. Dmitry comes to us with over 26 years experience in the MV world, specialising in switchgear, transformers, vacuum circuit breakers, enclosure design, kiosks, and much, much more. So Dmitry, thank you for coming on down and participating in today's webinar. Look forward to your contributions.
Thank you, Nick. My pleasure.
Excellent. Now what we're going to do is cross over to Queensland. We're going to go up north to Queensland where we have Kim Kamat. Kim's going to be giving us his insights on the world of MV. He comes to us with over 12 years experience, specialising in HV protection systems. So big hello to you as well,
Morning.
Kim.
Hello, Nicholas.
And now we're going to cross, we're going international, we're going over the Dutch. And we're going to be talking with the granddaddy of transformers, Mr. Sean Robinson. Hello, Sean.
Hello there, Nick.
Now, Sean, you've got well over 40 years experience with design, manufacture, testing, commissioning, troubleshooting, just about anything to do with transformers. So I think you've got quite a bit that you're going to be commenting on today with us. So thanks for coming along.
My pleasure. Looking forward to it.
Okay, now this is part one of a three-part medium voltage transformer series of webinars that we're going to be conducting, where the aim here is to try and demystify transformers. And today we're going to be starting with webinar number one, which is dry versus oil transformers. We'll look at some of the technical differences, the applications, some of the specification points that you want to look at if you're going to try and purchase or specify a transformer. And then we're going to wrap it up with a controversial panel discussion. And the question is, do oil transformers introduce a significant fire risk? So we'll see what people have to say about that. Also coming up then in November, webinar number two, we'll be looking at power outputs and enclosure design for transformers. And then webinar three will be focusing on designing for harsh environments. So quite a few interesting discussions coming up over the next 3 months relating to medium voltage transformers. Okay, well let's get straight into it now. We'll start by talking about cast resin transformers as our first technology, and we'll look at some of the basic key characteristics of these transformers and work our way through them. So I'm going to hand over to Kim, and he'll have a talk to us about those. Over to you, Kim.
Thanks, Nick. Yeah, so as Nick mentioned, we're just talking high level about some of the main features of dry type transformers. Or firstly, the transformers we're referring here are cast resin dry types, because there are various types of dry type transformers, but we're specifically talking about cast resin transformers. Now, generally in the industry, you will come across ratings of voltages between 3.3 kV to maybe about 52 kV. And up to about 20 MVA in size, which is getting quite large, but that's the ratings they get up to these days. Now, if you look at cast resin transformers, they have been around for a little while, even contrary to what some people might say or think. As we call it, they're probably going through a bit of midlife crisis. They're about in the age of about 30, 40 years, or probably approaching 50 in some cases. Where they're getting into newer and more advanced technologies, which we'll talk about in the next few webinars. The technology we're referring to here is the cast vacuum type transformer, dry type transformers, which essentially the resin is cast in vacuum. And I think there is some content that we'll mention later down in one of the presentations around this topic. Which we'll elaborate on. Now, one of the beauties of having a cast resin dry type is also the resin used is self-extinguishing, and it is designed to be fire retardant, which is also something we'll mention and unpack in one of the other webinars down the track. One of the comments that comes up, obviously, as we mentioned, is they do have these days a long service life. Now, what does long mean? How does it relate to other dry types or oils? We have Dimitri, who's going to elaborate a little bit more on that. And over to you, Dimitri.
Thank you, Kim. So design life of cast resin transformers obviously depends a lot on the application. You have to make sure that transformer operates within the resin temperature limits, and all this done through design as well as protection devices. But there's other important consideration for service life is the quality of the resin itself. And the best way to check or detect the quality of the resin in practice is the partial discharge testing, which is a standard routine test for cast resin transformers. Now, with the industry typical transformers and which are compliant to requirements of the standards, the partial discharge levels go up to 10 picocoulomb. With the best technologies available in the market, though, you can achieve a low partial discharge down to 5 picocoulomb or less. And this is where that indicates high quality of the resin, less impurities, less air bubbles, so on. And that results by estimates of our supply in a longer service life by 3 to 5 years compared to a normal technology. And this is where the technological process is extremely important, and that is the know-how of the manufacturers, how to achieve that. So therefore, we're talking really about the service life, typically 25 to 30 years in the industry. With our technology, we can offer up to 35 years service life for cast resin transformers.
Mm. So when you say long service life, we're really talking cast resin versus cast resin. At this point, we're not really comparing it to oil. Is that right?
Yeah, that's correct. The technologies, dry type versus oil, are so different. They're not comparable with regards to service life. And yeah, we can cover oil transformers service life later, but it is generally considered as longer because you're able to monitor and replace the oil in the oil transformer. But when we're comparing cast resin to cast resin, this is where that partial discharge becomes very important factor. Mm-hmm. The other point to mention about cast resin transformers is the low voltage winding. Now, it's typically made out of pre-impregnated material, which is also cured in the oven and becomes like one solid structure. It's not the same as a HV winding. It's not a fully cast resin, even though for low voltage that's well sufficient, considering the voltage levels or the electric fields are much less in the LV windings. But it still provides a very good mechanical strength for the short circuit events. Having said that, there is a possibility to cast the LV winding fully in resin in the same technology as high voltage winding, and that could be done for more extreme environments where you want the best possible environmental protection of that winding. But that, of course, would increase the cost.
Okay, now thanks, Dimitri. What's the typical maintenance requirements for cast resin transformers?
Yeah, so typical maintenance requirements, they will really depend on installation environment. Of course, for every cast resin transformer, from time to time, the tightness of all the bolts have to be checked, and they need to be torqued to make sure there's no loose connections, especially in the core and so on. But the other factor that will change a lot, it's a dust. So as such, cast resin transformers are not ideal for dust environment, and this is where it can result in quite frequent maintenance and removing the dust. But in general, clean installation environments, especially in the indoor, that's really a very minimum requirement for the dust cleaning. So as such, and other than that, there's no maintenance activities. The only other one is just a visual inspection of the transformer, make sure there's nothing suspicious, and the testing of the protection over temperature protection relay. So as you can see, requirements pretty minimal, especially if the environment is clean.
Dimitri, a lot of people sometimes think that the cast resin is a more expensive option, where here we're saying it's reasonably cost competitive. So from a cast resin to oil situation, generally you find in the market that cast resin's pretty competitive.
Yeah, actually they are, and maybe the opposite was the case in the earlier days of this cast resin technology, but now they became, worldwide accepted for the last, or at least 20 years, and produced in mass quantities in different countries, and really the cost, what we're seeing these days, is less for the cast resin than for the oil transformer, and it can be substantially less.
Oh wow.
So really, when we're talking about applications for cast resin technology, we're talking about indoor environments, and that could be various types of buildings, data centers, hospitals, airports, infrastructure, and residential. The obvious big advantage of cast resin is fire retardant material and non-flammable material that is used, so it certainly reduces fire risk a lot in the buildings. That is critical. For the outdoor environments, cast resin transformers has been used a lot these days as well. If the environment is reasonably clean, so there's no dust, especially conductive dust, and they're even suitable for installations close to the sea, depending on the type of testing that was performed on this transformer for environmental categories, which we'll talk about in our next webinar, but where the cast resin are not really good, like I mentioned, dust environment, conductive dust, mining, those areas, you have to be careful. There's no one rule, whether it's good or not, just have to look at the environment.
So Dimitri, I've just got an email come through from a person who's currently watching, and you've said there, about salt mist and water. They wanted to know, is it possible, or is there a problem in actually putting this on the beach?
Yeah,
literally, and I've seen this before. That sometimes you have the transformers; they'll try and put them right on the sand. Is that something that you can do? And what do the ratings tell us?
Yeah. Look, that's a very good question indeed. Really, I wouldn't put the cast resin transformer straight on the beach. However, there is some very comprehensive testing that cast resin transformers can go through, and we do have it in our range, which is E3 environmental category. It proves that transformer can operate under condensation conditions near the seawater. So that's a big tick. Of course, you have to consider protection against corrosion of all the parts, especially the core, and there are different measures that can be taken to protect against corrosion. So it's possible to install them closer to the water. Just have to provide a good level of protection.
Okay, all right, excellent. All right, so that's a pretty good overview of the cast resin transformer. What we're going to do now is, because we're here in the Power Hub, we're going to cross over to one of our medium voltage engineers, Shabnam Sadegh, and she's currently in front of our cast resin transformer that's on display, and she's going to take us through a little bit about the physical construction and some of the key points on the construction side of the cast resin transformer. Over to you, Shabnam.
Thanks, Nick. Here we are going to talk about the physical construction of a cast resin transformer. What we have here is a HV winding, which is cast in resin monoblock. That's the LV winding, and that's a magnetic core. What we have here is temperature monitoring probes in LV winding. These are the HV terminals, and this is offload tap changer. And if you come the other side of the transformer, I'm going to show you the LV terminals. These are the LV terminals, and this is the welded lifting point for cast resin transformer. Back to you, Nick.
Okay, that was great, great, Shabnam. Now let's have a look at hot and cold environments. We've got two, I think they're pretty interesting examples of places that you normally wouldn't think about putting transformers, but in these two examples, we did actually supply cast resin transformers. The first one is to the Australian Antarctic Division. They purchased a few cast resin transformers, and as you can see, it's pretty cold down there. Very cold indeed. So, Dimitri, you had a bit to do with this project. What were some of the considerations and challenges that had to be addressed in order to supply this infrastructure to these down there?
Yeah, there certainly were challenges, and of course, the challenge there is the negative temperatures that can go obviously below -40 and -50. Now, the cast resin transformers were designed and tested to class C2, which is -25. So it is pretty cold, but maybe still not good enough to install outside in Antarctica. Therefore, what we did, we just installed the resistive heater inside the IP56 sealed enclosure, and that maintains the reasonable temperature for this transformer. So really, this was the specific of Antarctica application. And I'll hand over to Kim to talk about another extreme example of cast resin transformer installation in Australia.
Thanks, Dimitri. Yeah, so another extreme, from one extreme to another. Talk about an application, Alice Springs, which is, as some of you know, or most of you should know, it's in the middle of nowhere, pretty much in the red earth. And it can get pretty hot there. So in that case, the customer specifically wanted a dry type transformer because of as some of the features we mentioned earlier. There was no switch room or anything like that it was going into, so it was an outdoor dry type installation. So a couple of the main considerations we had was obviously IP rating of the enclosures and designed to still cater for the full load, which in this case it was 6 MVA. Which is quite a large, transformer in general. So the transformer had to be derated to or rated for a higher ambient temperature. I think in this case it was 50 degrees. And also there was a fan arrangement, which was an N+1 fail-safe arrangement to cater for that, for the airflow requirements as well for this transformer. So contrary to some of the things where transformers, dry type transformers or cast resin transformers have to be in a clean or an indoor environment, here are a couple of cases where they are in very extreme and arduous conditions, but designed for those conditions, as Dimitri mentioned earlier as well. Thanks, Dimitri.
Okay, let's have a look at a transformer technology that I feel is probably not that well understood or spoken about here in Australia, and that's the amorphous cast resin type of transformer. So we thought it'd be useful just to point out that it exists and where you can use it. So let's have a little bit of a talk about this fairly unique beast.
Thanks, Nick. Yeah, so another thing with cast resin transformers, or transformers in general, amorphous core is something that's been talked about for many, many years. Essentially what it is a transformer has two main types of losses. You've got no load losses, which are your core losses, and your load losses, which are your coil or copper losses, as they're referred to. Here, by using an amorphous core, which is a structure which is different to the atomic structure of a standard laminated sheet steel, and that's what gives it the less hysteresis losses, which in turn reduces your no-load losses by about 70%. So it's a significant reduction over the lifetime of the transformer, say if it was 30 years. I would like to pass on to Sean, which had a couple of good examples that he wanted to share with us around this type of technology. So over to you, Sean.
Yeah, often the question that gets asked is, where do you use the different types of transformers and what's the advantages and disadvantages? One of the projects that I've been involved in just recently is looking at the possibility of using amorphous core transformers in Antarctica. Now, part of the rationale here is that obviously with diesel generation, the cost of getting the diesel to Antarctica and the CO2 levels and everything, anything that can be done to reduce the losses of the network are seriously looked at. And so in this case, amorphous core technology is being considered for that application. Also, I know in other instances where the cost of generation is very high, then the initial extra cost you pay for the amorphous core starts to pay for itself over the life of the transformer. Back to you, Nick.
That's a summary there of the cast resin transformers. Let's have a talk about the oil immerse designs. Let's just go through some of the basics to start with. Kim?
Thanks, Nick. Yeah, so really quite a mature technology. In Australia, probably commonly up to about, in transmission power stations or transmission stations, you would see them up to 220 kV and beyond, and maybe as large as 300 MVA. I've come across myself working in HVDC applications previously, up to about 220 MVA size single phase transformers, so they can get very large, also very complex depending on the type of application. But they are a very mature technology, meaning they've been around for a very, very, very long time. There are lots of different oil options as well that have been introduced over the years. And a lot of this is around safety. One of the common ones these days, the standard mineral oil transformer. And then you could have a Canaan version, which is a high flash point oil transformer. There are a couple of different options with high flash point oils, which can be either a synthetic version or a soy ester based version as well, which is more environmentally friendly. Dimitri, you had some good points to talk about around a couple of other things around oil transformers.
Thanks, Kim. There are two main technologies within the oil transformer family. One is a conservator type, and the other is hermetically sealed. The hermetically sealed name tells us it's fully sealed. There's no contact between oil and the air. This technology is used predominantly in smaller power distribution transformers, which go normally up to 3 MVA, but we've seen that hermetically sealed technology going up to 6 to 7 MVA, and really the demarcation line there is where you can have welded fins. And this is where you can still have the hermetically sealed transformer. So the advantage of such transformer over conservator type, that the oil deteriorates much slower because it's not in contact with oxygen. The larger power transformers, though, they have to be conservator type, where you have an additional conservator, which is an additional tank which allows oil to expand and contract depending on the temperature of the transformer. And this is where the oil level goes up and down, but oil is in contact with air in that case. So it's not possible to do otherwise for these larger transformers. So there are more specific requirements for their more frequent testing, more protections. But if we talk about the distribution transformers or transformers up to 6 to 7 MVA, with a hermetically sealed transformer, there's also a number of protection devices. Oil is not in contact with oxygen. There's still lots of cases, lots of possibilities for the faults. And this is where we want to monitor not just temperature, which is pretty standard, but also we want to monitor pressure and also the oil level and the gas detection. And there are devices in the market such as DGP-2 or similar types, which provide 4 protections in one device. So low oil, high temperature, high pressure, and the gas detection. And of course, it's important to detect any developing faults like internal arcing faults early on, so it doesn't lead to catastrophic failure of transformer, which, as we're going to see in a few slides, may even result in a fire. But the purpose of this device is to prevent those faults early on and trip the HV circuit breaker. Now, for the old transformer technology as such, it's a longer service life, goes up to 50 years, provided it's correctly maintained. The key to transformer reliability and performance is condition of its oil, and that condition can be easily tested. There's well-known methods how to determine that and what those different impurities or components in the oil indicate different types of faults. So all this very well known in the industry, by decided at which point the oil needs to be refined or even replaced with a new oil, and then extend its service life. Of course, there are other components like gaskets, which deteriorate over time and could lead to leakages. Again, they can be replaced, and this way, the life of oil transformers can be maintained up to 50 years. This is what we've seen pretty commonly in the industry, or sometimes they will even go over 50 years.
What about this next point here, Dimitri? Bulletproof. I think your comment is a tank is a tank.
Yeah, that's exactly right. We call a tank is a tank. So there's a couple of aspects to that. One is that obviously all the HV components of the transformer is protected by the metal tank from environment. The other thing, you have the oil inside the transformer, which allows cooling of HV winding as the core evenly and very efficiently. The other important factor with all transformers, they're very resilient to the over voltages, because if there is a network over voltage, for example, it will result in momentarily breakdown in the oil. However, the oil dielectric properties will restore very quickly, because it will naturally mix up, and all those carbon will go away from that point of fault. So therefore, essentially, all transformers are self-healing after their over voltage events, which won't be the case, by the way, in the cast-raising transformer. So that's why we're saying it's pretty bulletproof. Maybe Sean can also expand on that.
Yeah, probably 35 years ago, I saw this transformer come back to the factory, and there was a bit of a story about this transformer. So stormy night, car comes around the corner and takes out a 300 kVA pad mount on the side of the road. Now, that event actually resulted in a fireball, and the guys, once had got the fire out and got the transformer off the pad, they went back to the depot to get a replacement transformer. Unfortunately, the only transformer available was 100 kVA, so they decided that they would put it temporarily in place and go back and replace it with the proper transformer at a later date. Unfortunately, the next day, the guys were called into a meeting and told that they were going to be made redundant. So everybody forgot about this poor 100 kVA transformer sitting where a 300 used to be. And eventually this transformer cooked itself and got to a stage where the paint was peeling off the outside of the tank. I remember an article in the local paper where a school kid had burnt his hand on it. It had got that hot. I remember opening up this transformer and looking inside, and there was just black sludge inside the transformer. In actual fact, it had got down below the top of the windings, and even to this day, I am absolutely amazed that transformer had not arced. It was like, as the oil had just cooked itself, it coated everything, and yeah, that transformer did not catch fire, it did not explode. So there's an example, very extreme one, mind you, of a transformer that ended up being bulletproof, even though the load on it was 3 times what it was designed to handle.
Wow, that's unbelievable, isn't it?
Yeah, thank you, Sean. That's a very impressive example.
All right, well, let's quickly have a look at the typical applications and then some of the obvious limitations when it comes to oil transformers. Dimitri.
Yes, so the typical applications are outdoor. Yeah, the transformers can be used pretty much everywhere. They have advantages in the outdoor applications because, like we said, the HV components are fully protected. They're inside the steel tank, so therefore it's not sensitive to any corrosive environment. Of course, the paint has to be used of a proper standard to withstand those environments, but that is achievable. So therefore, dust applications as well, the oil transformer certainly has advantage over cast resin. Therefore, they're so popular in the mining industry. Now, oil transformers, of course, before the cast resin technology became more popular and mature, they used a lot indoors as well. But as we're going to talk in the next slide, because they present substantial fire risk these days, customers prefer minimize their use indoors. And especially that requirement also comes from insurance companies who don't want to see oil transformers used indoors.
Okay, all right. So just to make it nice and simple, we've got a summary slide here. So let's just very quickly run through this, and people can obviously have a look at this in their own time. So Dimitri, let's just look at some of the highlights here and discuss those.
Yeah, so the important point, like we already mentioned, fire safety. Certainly, it's higher for cast resin transformers. We're talking about maintenance cost. If you compare cast resin and hermetically sealed oil, they're probably the same, low to medium maintenance cost. And if you look at the power transformers, of course, their maintenance cost goes up because more frequent oil testing. Diagnostics on site, you can diagnose cast resin transformer, though it's quite expensive methods where you can measure partial discharge on site. With oil transformers, there are more methods, more readily available, and especially if you check the oil quality, where we compare oil to the human's blood, from a simple blood test, the doctor can tell lots of things about our body, and same for the oil in the transformer. Environmental risk, certainly benefit with the cast resin that it doesn't present any environmental risk, while the oil transformer has always a risk of oil leaking, and therefore special measures have to be taken, such as oil bonding. Physically, cast resin transformers are slightly larger per MVA versus the oil transformer. With the over voltages, like I already mentioned, there's more risks for cast resin transformers because the over voltage event that exceeds the BIL level of the insulation will result in a catastrophic fault of this insulation. For using surge arrest is very important, while the oil transformers actually self-healing in event of over voltage. Outdoor applications, we already mentioned oil transformers have an advantage, though cast resin can be well used with outdoor enclosure in suitable environments. And that links also to environmental categories such as E2 and E3, which allow to use cast resin transformers in more humid environments or close to the seawater.
Just an interesting, we'll just get into the efficiency discussion, because this one I think is often again misunderstood, but is quite important. So we've got their efficiency, and we've got this acronym in there, MEPS. And I think, as Sean will point out, there's another one called HEPS later on that sounds like something you want to see the doctor about, but rest assured it's not. Put some cream on it, it'll be fine. What do we know about efficiencies, and what does this mean? MEPS and typically 99%. What are we talking about there?
Well, it's interesting because one of the comments that I hear quite often is, oh, well, cast resin transformers aren't quite as efficient as oil. And it's true. And the minimum efficiency performance standard caters for that. But you've also kind of got to put it in perspective. So if we're talking about 1,000 kVA, an oil transformer, its minimum efficiency, 27. For a dry type, 99.03. So they're still both over 99% efficient, and the difference between them is not that great. Interesting that the standard also allows people to specify a higher efficiency as opposed to the minimum. But the reality is that you don't often see it being specified. And part of the reason for that is that as you try to make transformers more and more efficient, it's the law of diminishing returns. So yes, you can go to domain refined steels and lower loss steels, and you can do all sorts of things, but at the end of the day, you're trying to crib 0.1, 0.2% in order to go from minimum to a higher efficiency. And with that, the cost of the transformer goes up. So interesting debate.
All right, well, that sums up the difference between the two. Before we go on, again, I'm just going to cross over to Shabnam. She's going to take us through the physical construction of a oil transformer that we have here in the Power Hub. So over to you, Shabnam.
Thanks, Nick. Here we are going to look at some of the physical construction of oil transformer. What we have here is an oil tank. These are HV terminals using plug-in bushing with screen elbow connections. These are cooling fins. That's TGPT2, which is the protection device, integrated protection device, which is checking and monitoring all temperature, pressure, and oil level. That's offload tap changer. That one is welded lifting point for the oil transformer. That's the safety valve, and that's the LV cable box. Thank you. Back to you, Nick.
All right. So if I was an end user or a consultant trying to specify a transformer, we just wanted to quickly run through some of the key characteristics that you really want to make sure that you're putting in your specification. Let's have a look at some of these key specification points that you should focus on.
Some of the main things to consider. So as you can see on the slide, there's a lot of different ratings or different standards. That's mainly coming out of the AS 60076 standard and some out of the IEC, depending on what type of transformer you look at. So those are some of the standard considerations that you should refer to within your specifications. But the main other parameters to look at are obviously voltage, your power ratings, your impedance. If you have a tapping range in mind, vector grouping, depending on where it's going and which network it's connecting to, because sometimes depending on the where you are around Australia or New Zealand, the vector grouping can be different depending on the utility it's connected to. Winding materials, that's another interesting debatable topic, and I think Sean has a good example about that, which he wanted to mention. So I'll pass you on to Sean.
Yeah, thank you, Kim. It's very interesting for me because I used to see a lot of specifications where copper was specified, a lot of consultant specifications basically saying that the winding materials had to be copper. I used to make the point that I could design you a bad transformer using copper just as easily as I could design you a good transformer using aluminium. You know, the materials are different, but as long as your processes and your design parameters cater for those differences. So for instance, the current density for copper is higher compared to aluminium. So as long as you take those design parameters into consideration, it really doesn't matter which material you use. Having said that, especially when we come to the cast resin transformers, a lot of the manufacturers have a real preference for using aluminium conductor. And the simple reason for this is that the coefficient of expansion of aluminium compared to the cast resin materials that are used are very, very similar. And so therefore the thermal stresses within the winding as the transformer cycles through different loads and heats and contracts means that the thermal stresses are very, very even with the conductor versus the insulation material. Just something to bear in mind. You can have a good and a bad transformer in either material.
Interesting. Thanks, Sean. That's a very, very good point. Moving on, IP ratings. There can be lots of different IP ratings and environmental conditions, as we briefly mentioned before, but also at the same time, it will be covered off in one of the next upcoming webinars, and we'll unpack that a little bit further. With regards to classes. There are different classes around environmental classes, which Dimitri mentioned. Also Dimitri earlier mentioned around the climate conditions, which are more referring to again cast resin transformers. There's also a fire classification with regards to the same type of transformers as well. And then one of the other parameters that comes into play is sound levels, because especially for indoor applications, that could be a point of consideration, and it is something that's mentioned in standards again. Power output, obviously the continuous power output of the transformer is what you want to look at. Dimitri, did you want to elaborate? You want to elaborate on that point? Thank you.
Yeah. So with the power output of transformers, it's probably evident to most of people that whatever is on the nameplate of transformer, as shown as a rated power, this is what you should expect as a transformer output in all conditions. And actually, the good thing, it is the case when talk about transformers on their own. So regardless if transformer is within enclosure or without enclosure, it still must deliver 100% output, as per 60076 standard. However, there is important difference we need to understand. Enclosed transformer versus a kiosk substation, where you can have a transformer along with other equipment such as HV switchgear and LV switchgear in one packaged kiosk. And this is where the different standard applies, such as 62271 part 202, and that dictates different requirements that allows actually derating of transformers within a kiosk. So transformer doesn't have to deliver the full output. So that's a key difference we have to understand. But as far as we go, just a transformer on its own, it's always 100% regardless of enclosure.
Thanks, Dimitri. And we will unpack some of those further down in a couple of the other webinars coming up. So stay tuned for that. Another point mentioned there is ambient temperatures and monitoring, obviously, with as Dimitri also mentioned earlier, with oil transformers and with cast resin transformers, there are temperature monitoring techniques and devices that are available, and the transformers have to be designed to the right conditions as well. So as you saw in a couple of the extreme examples we had for you earlier in this webinar. Something else to consider is around arc flash mitigation techniques especially when it comes to cast resin dry type transformer for outdoor applications. There might be additional considerations. You might have types of oil. As I mentioned earlier in one of the slides, there are different types of oil available for oil transformers. So it is again mentioned in the standard and also in the substation 2067 standard, depending on where the transformer is located. So that's something to also bear in mind. And last but not the least, partial discharge is obviously one of the main routine tests that's conducted for a cast resin transformer. So it is an important parameter when it comes to measuring the life of your cast resin transformer. Thank you, Nick. Over to you.
Certainly is. Okay, well, we're almost at the end of today's webinar, and we're going to finish up with what we call the controversial panel discussion. And today's question is, do oil transformers present a serious fire risk? I'm going to play a quick video. This is some recent footage in the last couple of years of two different events where we've had oil transformer fires, both based in New South Wales. So let's have a look at these. And here you go. So this is next to an apartment building, and we've got an oil transformer and a kiosk here. And as you can see, quite intense flames, lots of smoke. And then in this case here, it's a substation fire, so obviously a much larger transformer, and you can see that's some serious flames going on there. So yeah, that doesn't look very good. But what do we see from the cast resin side of it? So here's a photo taken from a site where there was an internal fault within a cast resin transformer, and as you can see, there's a hole that's been punched through the material. Looks like a lot of heat has been generated there. A lot of blackening, carbon and soot and other things there. So, Dimitri, maybe if we have a look at this, it doesn't look anywhere near as dramatic as what we saw in the video. But what can you tell us about this this example? What happened with this cast prison transformer, and maybe why didn't it go the same way as the oil transformer video we just saw?
Yep. Thank you, Nick. Yeah, that's a very good example of how cast resin transformer behaves in the event of the internal fault. And the main factor to keep in mind is calorific energy available in that device. So as we know, oil is highly flammable material and has plenty of calorific energy in it. If the fire started in oil transformer, it actually cannot be even extinguished by a fire brigade. They have to wait till the whole oil burns out. Now, the difference with the cast resin transformer, that the significant damage will occur while there is electrical fault, electrical arcing fault still happening. But that is a very short event, because the electrical arcing fault going to be cleared by upstream protection in generally less than a second. And then after that, the fire extinguishing, fire retardant properties of the cast resin material kick in. And what happens that once the external source of that fault was removed, such as clearing the electrical fault, from that point, the cast resin material will not support burning. It's so-called endothermic process where, it doesn't produce energy when it burns. Therefore, the burning very quickly stops. And there's a special test called a fire behavior test for the class F1, which actually checks the behavior of this resin after the external fire event was removed and stopped. So it proves that the resin is self-extinguishing material. This is why we can see there is a bit of black carbon around, but that was the result of that initial electrical arcing fault, and nothing really happened after that. You can even see the cables near the transformer, they're still intact down the bottom. Therefore, there was not any fire going on after the electrical fault. So that's a key difference between oil and cast resin, and therefore is well reflected in AS2067 standard with regards to installation requirements, where the cast resin transformers requirements for fire protection, fire clearances are significantly less than for the oil transformers. And yeah, you can read the standard for details.
Interesting point. So the thing we did bring up previously is we said the oil transformer was bulletproof, though. So in the event, like the likelihood, I think you've got a saying, with the oil transformers, the chances of it going wrong are very, very low. But when they do go wrong, it could be quite significant in that case, can't it?
Yeah, exactly. Low probability but high consequences.
There we go. That's a better way to put it. Sean, you've obviously being the granddaddy of oil transformers, you probably have a few things to say about this question. Do oil transformers present a serious fire risk? What are your thoughts on it?
I guess one way of looking at it, especially with the cast resin materials being self-extinguishing, we can look at that as being an endothermic reaction. So, in other words, we as long as there is power on the transformer causing arcing or whatever the event might be, the reaction will happen. But as soon as that source is removed, then it extinguishes itself, and the result is what you see on the screen there. Oil transformer, we can kind of think of it more as an exothermic reaction. Now, we talked about the fact that transformers are bulletproof, and I gave the example of one where the transformer had literally, the oil had got down below the top of the coil and it still hadn't gone bang. Now, part of the reason for that is that if you just simply think about a fire triangle, we need a source of material to burn, we need heat and we need air. And I think in the example I gave before, the only reason the transformer didn't go bang is because it was sealed and the tank didn't actually rupture. There wasn't actually an arcing event in that particular case. And so therefore the fire didn't start. But once, as you mentioned, Dimitri, once a fire starts and air is feeding that oil fire, it just continues on its own. You can trip your HV protection, you can do whatever you like, but that exothermic reaction just keeps happening until there is no material left to burn. And an example, a very extreme one, I have to admit, but a number of years ago, there was, I think from memory, 800 to about 1,000 kVA wind farm transformer. And it had been noted over a period of time that one of the HV A-type bushing wells was leaking. And it was noted that at some stage they needed to carry out some maintenance. Unfortunately, what happened is the oil level actually dropped below the top of the tap switch, dropped below the top of the bushings, and there was quite a catastrophic arcing event, split the tank open. And yeah, the photos were quite horrendous. Literally a tank with all four sides split open, a burnt out core coil assembly sitting in the middle of a paddock. You know, very, very extreme. And as we said, you know, they don't often happen, but the consequences of when the oil does actually ignite and does start burning, the consequences are very high.
Mm. So
Definitely worth thinking about.
Definitely. All right. Well, that's some very good input there, Sean. Thank you very much for that. Any other comments before we put this one to bed, Kim?
No, I think you guys, Dimitri and Sean, have covered them pretty much. Yeah, on the spot. It is really, it's not that straightforward. It's horses for courses. Every application is different. And we've got to think about where these transformers are going in and what are the risks overall. So no different to what we do in arc flash safety. It's very, very, very similar. So it's really depending on, because the same thing applies. You know, the risk of it is happening is low, but if it does happen, the consequence is very high. So that's why it's an important discussion. Thanks, Nick.
All right, well, let's wrap things up. That hopefully that has given everyone a bit of an idea around, you know, cast resin transformers, oil transformers. We're going to open up the lines fairly soon to take some questions from people who are online and listening and attending this webinar. So we'll try and read those out and do our very best to answer those to the best of our ability. And obviously with Sean being here, he knows pretty much everything that's ever been written. So we feel pretty confident about that. Don't forget, of course, coming up in November, webinar number 2 in this 3-part series. As I mentioned earlier, looking at power outputs, enclosure design, looking at IP ratings, and we will also have a super controversial panel discussion looking at dual ratings on transformers, and can you simply slap a couple of fans onto a transformer and dramatically improve its performance? Who knows? We will see. Now, if you would like to know more, if you'd like to come and have a look at some of the medium voltage products, low voltage products, motor control, automation, safety, and much, much more, come and visit us in the Power Hub, located in the NHP head office here in Richmond, Victoria, but also in Sydney, South Australia, Brisbane. We also have mini power hubs set up as well. So if you can't make the journey all the way down to Melbourne, get in touch with the local branch and they can certainly show you some of the products and do some demonstrations. So thank you everyone for helping out today. It was great. Thanks Dimitri, Sean, and Kim and Shabnam for your help on this, and look forward to catching up with you in November in round 2.
Thank you.
Yes.